Hi, everyone. Just a reminder that if you haven't signed up for what was I calling it? An interview, then please go to Canvas and sign up there. I can resend out that link, but only a little over half of you have come and talked to me. We have the whole week, so there's no rush, but I just want to make sure everybody makes sure to sign up for some time. And if you missed your meeting, that's fine. Just sign up for another one, no problem. Okay. Other questions?
Is the best way to prepare for the interview to just go over the like solutions to the homework?
Yes.
Okay.
All right. Anything else? Not management wise. What do I usually call it? Bookkeeping wise. Okay. Okay. Then I guess maybe just get to it. There's actually two terms that I forgot to define and two topics that in a usual 10-week class we would have seen. I wanted to just, do the two terms that I forgot to define. And then for the current sources and the op amps, just really quickly, like maybe spend, less than 10 minutes each on each of them, just so you've heard of them. And you can go back and look them up later. But terms I forgot to define is phase margin and gain margin. And if you've had 302, you probably are comfortable with these terms, but just to be complete here, the phase margin and gain margin, that talks about when you have an op amp and you have two poles. This isn't drawn very well for two poles, but that at some point over here there's a two poles to cause this 180 degrees phase shift here. But the phase margin is where you get to 0 dB, you draw a line down to hit the phase, and then draw a line over, and this might be minus 150, and you look at the difference between this phase right here and 180. So it's how far away from 180 are you at this point? So again, you find 0 dB, draw a line down, and how far away you are from 180, from 180 degrees phase shift. And the phase margin, it's, let's see if I have that. If you have a phase margin of about 60 degrees, it looks like your regular Bode plot. But if you have less than that, then it gets closer and closer. The positive feedback gets larger and larger, and you get these bumps until really large spikes right at this point. So about 60 degrees phase shift. A lot of people design for 45 to 60. So there aren't like major spikes on when you look at the frequency response. So that's phase margin. Gain margin is at 180 degrees phase shift. How much below 0 dB are you? Okay, so at 180, so gain margin is where you find where the gain is 0 dB and go down and find the phase. Gain margin is where you find you have 180 degrees phase shift and you go up and look at the gain. So those are two terms. Any questions on those terms? Again, they're just a quick way to, somebody can say, oh, I have a phase margin of 45 degrees, and you know, oh, okay, so you've got two poles. When you get, when you're at 0 dB, which is the safe point, you have this many, the phase is this much away from 180. So it's a quick way to say all that with one term. Is that good? Okay, I don't see any questions on that. I put it on put this on. Never updated the page, did I? I put this on down here for the final class. If you look on phase margin and gain margin, that's that page that I just showed you. Okay, so we've already checked one off. So should we put a nice little green check? I was listening to something on NPR about to-do lists and how to do them well. And always give yourself something you can check off easy. So that. Okay, slew rate. Slew rate is, you probably saw it in lab. You may have seen it in lab. But if you have a circuit, and if you remember from 307, there's the rise time and fall time. So you would do something like this on the input and then see how quickly the output goes up, or do the other direction and see how fast it goes down. Or if it's inverting, then these two would be switched. And then this time from 10 to 90 for digital, or 90 to 10, was the rise time or fall time. Okay, slew rate is kind of the analog version of that. Slew rate says, okay, I'm going to change my input really fast and see how fast the output changes. But because analog isn't from a logic 0 to a logic 1, we're more interested in the slope. So the only difference between really rise time and fall time and slew rate is that this is, you look at the slope, and the slope is how many volts you change per unit time. Whereas this was the time from 10% to 90%, or the other direction. Okay. So this is, slew rate is measured generally experimentally, but say in the same way that rise time and fall time is determined, there's some capacitance on your output, and there's something putting current onto this or pulling current off of it. And if you remember that C over I, that equals your dV dt. So if somebody gave you your capacitance and you knew the current onto this node, you could find the slew rate here. So this is all slew rate here. Okay. So another thing you can find from the slew rate is how fast you can get an accurate output. And so let's say you're putting a cosine of a cosine as your input. So your input right here is cosine. And what you'd like to do is have that cosine come out on the other side. So let's see, if you look at a cosine, you can see its maximum change is right here and here and here. That's where you have the steepest slope in your cosine. So this right here, it's not changing very fast at all. So almost any circuit can keep up with that. But right here where it's changing really fast, you have those R's and C's inside your circuit, and it could get filtered out. So first thing you want to check is you want to take the derivative of this, and you want to find the maximum slope, slope max. So if you take the derivative of cosine, you get your 2 pi, oh, I forgot my f in here. 2 pi f times your sine of 2 pi f t. And then you want to find it where this is maximum. And then when sine equals 1, that's where your maximum. So what you end up with is the maximum slope here is actually 2 pi f. So to put a cosine, oh, I forgot amplitude. Oh, sorry, y'all. So I'll do this in a different color just because it's a update. So you have an amplitude here. And this is the steepest slope of your cosine. And you know that the slew rate is the steepest slope of your output. So slew rate's generally taking the steepest slope that you can get out of your output. So now you know the steepest slope you have to accommodate this sine wave right here. And you know the steepest slope that your circuit can output. And if you set those equal to each other, the steepest slope that you need and the steepest slope that your circuit can give, which is your slew rate, steepest slope that your circuit can give is slew rate. And that has to be greater than or equal to your 2 pi FA. For this particular sine wave, this is the steepest slope you'll see on it. And if you solve for frequency here, you get frequency is less than or equal to your slew rate over your 2 pi amplitude. And so this is another way. We've been using the R's and C's to figure out where you have a corner, and you know after that corner, your amplitude starts to drop or your gain starts to drop. This tells you, this is a different way to see what the fastest your circuit can run is. And just remember that the only signal that is composed of just a single frequency is a sine wave. Square wave, how many frequency components does a sine wave have? A square wave, sorry. How many frequency components does a square wave have?
Infinite, technically, right?
Infinite, yes. So that has so many different frequencies. You're not testing if a single frequency will work in your circuit. You've got so many frequencies, it's really hard to get information. So a sine wave is the only signal that is composed of just one frequency. And that's why it's used here to find your Fmax. And this frequency right here, this is the maximum frequency you can run your circuit at. So it is called Fmax. Okay. So just two different ways to go about finding the maximum frequency that your circuit can run. And this one, because slew rate is largely experimentally found, you put a function generator on the input and give it a really sharp change in input and watch the slope of the output. This is more of an experimental way to find your maximum frequency, whereas the RCs are the theoretical way to find your maximum frequency. So questions on that? I can't tell. I think maybe lots of you are studying for finals. Okay, so check slew rate. All right, we're moving right along. Let's do op amps for a second. Let's skip down here and get this one checked off. Okay, so that's slew rate up to here. So a couple of questions. What does cascoding do for you? Cascoding. What does cascode?
Increases R out.
Increases R out. And if you cascode a common emitter, what's the advantage you get? Okay.
Increased R out, increased gain, right?
Increased gain. So this increases gain. Okay. How about a diff pair? What nice things does a diff pair do for you? A differential pair.
It allows you to use differential inputs, right?
Okay. Differential inputs, and that's without that we couldn't make the op amps that we know. So that's what's super important. What else is it? What's its superpower? It has another superpower. What about noise?
Because it's a differential, the noise basically doesn't mean anything.
Yes, so input noise goes away. Input common mode noise, so noise that happens to both sides, it just goes away. Noise disappears. Okay, so we've got cascoding that has this nice increased gain, and we've got that differential pairs get rid of common noise. And if you, we won't go back over this right now, but if you look at a common emitter, if there's noise on the input, that changes VBE, and changing VBE changes the current a lot. So any noise on the input of a common emitter just totally destroys your result. It makes it so that the amplifier won't work correctly anymore. It won't give you an accurate output. So this is weak against noise, but you can cascode it and get a good gain. Differential pairs, it can solve that noise problem. So I'm going to draw something here. This may take a moment. Actually, I can draw it a slightly different way. I'm going to do that. Switch directions. So what's this do for you? It's kind of the best of both worlds. So what about gain for this compared to regular diff pair?
Significantly higher.
Significantly higher. And what about that problem that with the common emitters, so sensitive to noise?
Your input's balanced, so common mode noise gets canceled.
Common mode noise goes away. So this is actually a really well-known amplifier, and because it's all stretched out, it's called a telescopic op amp. And it's really not a complete op amp because the R out is so high. If you hook this up with feedback, something would fail. So this is really the input and gain stage of an op amp. But if you, just as a reminder, if you need to get rid of common mode noise, make it differential, whatever circuit you have. If you need a higher gain, you can cascode. And guess what? If you want more gain, what would you do? What else could you do here to improve this even some more? Should we do the sound game?
Would you lower the current down at the bottom?
That would increase Rin, but I don't know if it will increase the gain. And you want a high Rin for this, so that would be a good design decision. Yeah.
You can increase your positive and negative rails, right?
Probably. So in 431, EE 431, I don't know if anybody's going to take that in the fall, but there is for a particular transistor. So first, when you want to make an integrated circuit, you want to make a chip, you find a company that fabricates the chips, and you say, okay, what's the maximum voltage I can use? and they will give you a voltage, and you have to abide by that, or they won't guarantee the chip will work. So like we've had a 1.2 volt, 1.8 volt requirement from the fabricator. So often the rails, you can't really move the rails. But if you go up, remember passive load, then active load, then cascoding. What's the next one? Okay, remember gain boosting? Yeah, so you can actually make this even a bigger gain by gain boosting it. But this right here, this is a well-known type of amplifier right here. Okay, there's one more, and it actually will take, I'm going to go through it really quickly, just so you'll see it. But and if you want to stop me for question, that's fine. But otherwise, just so you have an opportunity to see it, I'm going to just like blaze through it. Yeah. So the weakness of the telescopic op amp is 1, 2, 3, 4, 5 transistors, at least 5 transistors that all have to be in the forward active region. And that means that your supply voltage probably has to be pretty high to accommodate at least 5 VCE sats plus whatever your output swing is. That's how high the supply voltage has to be. So there's a style of making amplifiers. Just try to make this smaller. There's a style of making amplifiers where you try to get almost the same amount of gain, but you try to use fewer transistors between the rails. And it's called folded. And this is a folded cascode. Folded cascoded amplifier. And what you do is, actually I should just make a video. I'm going to make a separate video, but just so you've heard of folded amplifiers, and there's all sorts of, there's folded Gilbert cells, there's folded rail-to-rail amplifiers. There's a lot of circuits are folded when there's too many transistors between the two rails. What you do is you take the input part, and I'll just draw it so you see it, and you fold it up like this. And then over here still, oops, over here is still cascoded, but you control the current. Okay, this is not going to work as a quick introduction, but you take the inputs over here. So this is your VI plus and your VI minus. I'll make a video to put that on my list. And these currents change the current through these bottom transistors, and therefore the current through the top. So instead of having the transistor that changes the current in series with all the other transistors, it's over here just either injecting current into a side or not injecting current into a side. And the top part here, like this will be fixed as at a constant current. And so if you turn down the current here, the current through up here goes up. If you turn up the current here, the current through the top transistors goes down. It still has to add up to a constant current. And that way, now you only have 1, 2, 3, 4 transistors between the rail and ground. And I know that just went way too fast and probably made no sense. But it's if you're ever designing something and you have too many transistors between the supply and ground, look up folded. See if you can fold that circuit. Put the input part of the circuit, pull it out to the side, and somehow, connect it up so you get the same behavior of your circuit. And again, I'll do a video. I don't have too many things embarrassing on this. Okay, but on to the actual topics of the day. So let's mark that off. There's also current sources on this list, and the thing that we were missing there is just a couple of the most famous current sources, and one is let's go back over here by seeing. So in lab and in class, we talked about degeneration. Where is the... If you use degeneration to change a current source, change the current through a current source, that is generally called a Widler current source. So we didn't put a name to using degeneration to change the current or turn down the current. But famously, the person that proposed this and described the math, which I'll also put in another video for those that want to look at that, is a person called Widler. So when you have a degenerated current source, you can call that a Widler current source. So we're done with one current source that I didn't put a name to. The math for this is actually really interesting, and in old versions of analog, computers, they used a trick. So I'll show that trick in the video for those that are interested. Okay, another type of current source that is well known is the Wilson current source. And though Mike Wilson is really smart, it's from before his time. And the Wilson current source, what it does is it kind of cascades. Does cascading give you a good current source? So what's cascading's superpower?
It increases your output resistance, right?
Yes.
So
And
that would be bad for a current source.
Is it though? So what does a big R out mean? When you change the voltage across a big resistor, does the current change a lot or a little?
Oh, just kidding. It's actually really good.
Yes. So anytime you can up the resistance, then it's a big deal. So Wilson realized that and said, well, cascading is too hard. And cascading is actually better than the Wilson current source. So I'm not quite sure why Wilson gets all this attention. But Wilson said, okay, well, let's do this. And I'm going to diode connect down here. Does anybody remember the resistance of a diode connected transistor? From all three terminals have the same resistance.
1/GM?
Yes, so it's a super little resistor. So this actually, it's like degeneration, but with a resistor of 10 ohms or something. So degeneration generally does better than the Wilson's current source, and cascading does better than a Wilson current source, but this is, I don't know why Wilson gets all the attention, but it's a well-known name, and you might hear it if you have an interview or something with that talks about current sources. Yeah, cascading is just, it takes up, again, you need all your transistors in the forward active region or saturation if it's a MOSFET. So it takes up a little bit of headroom, but this does too. So really cascading is, if you need a really good current source, just cascade some transistors and it's better than the Wilsons. But I wanted to bring up the name. So that went quickly. Any questions on Wilson's current sources? Again, I'll do a little video on this stuff too, for those that are interested, that need something to do over summer. Okay, then we are on to what our actual topic for the day is. Uh, so last time we talked about kind of a magic number, 1 plus t. And what's t called? Anybody remember from 302 or from the last lecture? Are you all studying for another final?
It's the loop gain.
Loop gain, yes. And what does it equal in terms of pieces of your circuit? So if you have
It's AV times F.
AV times F, yes. So it's your feedback factor times your gain of your actual op amp, AVF. Okay, and let's look at case one. So our case one with feedback is if AV isn't infinite. Remember, for an ideal op amp, infinite. R in equals infinity. R out equals 0. So these two are still ideal, R in and R out, but let's say AV isn't infinite. Okay. If you have, I should have done something else first, but got to here, so I'll keep going. If you have a voltage input amplifier and a voltage output amplifier, in other words, a voltage amplifier, if you have a voltage amplifier, do you like a high RN or do you like a low RN? Let's just make this really large, close to ideal, but not exactly ideal. So for a voltage input amplifier like we've been using all quarter, do we like a high RN or a low RN?
High RN.
High RN. So there's this magic thing that happens that when you hook a circuit up with feedback, your RN, your actual perceived RN after you've hooked up with feedback is actually 1 plus T times your original RN. And we'll talk about where that comes from in a minute, but just wanted to keep going with this 1 plus T. Okay, what about R out? I'll put feedback down there, as maybe that's clearer. So after you've hooked it up with feedback, do you want your R out to be small or large if you have a voltage output amplifier?
Small.
Small. So what happens is whatever your original R out was before you hooked it up with feedback, it actually gets smaller by a factor of 1 plus T. Now your gain with feedback always gets smaller, so your total gain actually equals, it's always divided by 1 plus T. But this 1 plus T, if your R in and R out are pretty close to ideal, your feedback just makes them better. It's kind of cool. If you have a low R out, say like 5 ohms, and you hook it up with feedback, you can get like 0.02 ohms or something perceived at your R out. So it's kind of magical there. So let's see if so to apply this, we need to figure out what R in and R out are, and your gain of your amplifier. So let's take, let's go back to, see which one was it? It was the feedback to post. Let's see if this is the right slides. These are the right slides. I think they are. So on Canvas, I have it in the final lecture place. I have slides on feedback to post. So if you want to follow along on the slides. And we'll get back to this slide. But so when you have an amplifier, and this is still an op amp, and it turns out that this is your VN plus, and this is your VN minus. So it's a different form than you've been seeing, but you can apply this same thing to the op amps that you've been using with the diff pair on the input. But let's since all my examples are with this kind of amplifier, let's use this one. And again, at this base right here, that's your input, and that's your VI plus, and this is your VI minus. And you can check that. This is a common emitter with, looks like degeneration here. So this, if I call this VI plus, if this goes up, since the common emitter's inverting, this will go down. Another common emitter, this will go up, and this is a follower, so this will also go up. So if this input goes up, V out goes up. So this is the VI plus input, and that's the VI minus input. Okay. All right. So since this is the way you find AV is you circle all the vanilla amplifiers. And again, that's my word, and nobody else will understand it, but it's the most basic version of the amplifier. So it's a common emitter with a passive load or common emitter with an active load. It doesn't include degeneration or cascoding. Well, I guess if it was cascoded, it would, the cascoded transistor would be considered a transistor. So it's just not with degeneration. That's the easiest way to say it. So right here, this looked like a common emitter with degeneration, but since degeneration is actually feedback, and we'll see that in a minute, but we'll get rid of the voltage source here. And the most basic version of this amplifier is a common emitter with a passive load. So I'm going to circle that. Okay. And then I go to the next stage. What's the simplest version of the next stage? Everyone's very quiet today.
A common emitter with passive load.
Yes, common emitter with passive load again. And then what's the next stage you see?
Common collector.
Common collector. And a common collector, this RL is part of the circuit, so you have to circle that whole thing. Okay, and now we've gone from the input to the output. This whole thing right here is your lowercase AV. So all this stuff in red, that's your AV. So what's the gain of a common emitter with a passive load?
Negative GM times RO in parallel with RQ1.
RQ1, perfect. And then what's the gain of your second stage?
The same thing except with RQ2.
GM, RO, RQ2. And then what's the gain of a common collector?
1.
1. And you're done. And I'm not including loading factor just because that would make it too awful. But that's your AV. Okay. To find your RN, you actually look at whatever the input's connected to. And input's connected here. And you don't worry about RE and RF. Just look at the vanilla amplifiers. So if you're just looking at a common emitter, what would the RN be? Just want to look at what's inside the red circle.
out in parallel with RQ1?
That's the R out, but what about the R in right here?
Oh, sorry, R pi.
R
Right.
pi, yes. And then for R out of your common collector, so you find V out and you just worry about the thing inside the red circle. What's your R out? What do you think?
Is it 1 over GM in parallel with RL?
Yes, and in theory, you can say RL is probably larger than 1 over GM, might be 1K, and 1 over GM might be 10 or something. So you can approximate it as 1 over GM. Okay, so I'll go back to the paint in a second, but now you have your, before taking feedback into account, you have your AV, you have your RN, and you have your R out. Those are the things that get multiplied by 1 plus T or get divided by 1 plus T. Okay. 1 over GM is probably pretty small, and R pi is probably pretty big, so it's an okay approximation. So, but we've got some stuff left over here. What do you think that stuff is? Think back to the 302 model where you've got the differencing, the circle that differences, then you have the AV, which we just found. And then what's left?
Some feedback?
Yes. So everything else, that's your AV, and whatever's left is your feedback. And so to find the feedback, the signal comes in from this side and goes towards the input. So it's going, your signal is going through your amplifier this way, but the feedback comes back from the output and goes back to the input. So this is actually your V in for your feedback. It's V out of your whole circuit, but it's V in for your feedback. And this is your V out of your feedback on this side. So what you want is, if you remember F, that feedback factor is actually a gain. It's, you have an input to your feedback block and you get an output of your feedback block. So the gain of this block is VO feedback over V in feedback. So if you have V out feedback, can you come up with an equation that uses V in? What's the circle in, what's the circuit inside the blue circle?
Voltage divider.
Voltage divider. So you can say, oh, that's a voltage divider. I know V in feedback is the input to the voltage divider. And this is your RE over your RE plus RF. But what you actually want is V out over V in. So if you divide both sides by V in, you get F equals RE over RE plus RF. And now you have all the values you need. If R in is pretty big and R out is pretty small, now you have all the values you need to come back. I'm going to keep that so we can come back to it. Go back to paint. Remember over here, we had we figured out that if Rn was pretty big, then Rn is 1 plus T times Rn. So let's do see if I can do it side by side. So we have our values for feedback. So if you apply this now, I don't want to write all this out, but we have the gain. We know it's 1 plus AV, and we have AV over here. That's your minus GM RO in parallel with RQ1 times minus GM RO RQ2. That's your AV. And now you have your feedback factor, which is RE over RE plus RF. And that's times your original Rn, which is R pi. Maybe I should. So magically, your Rn, which is R pi for your op amp, basically, gets multiplied by whatever your gain is of your op amp. And you've seen some gigantic gains in lab, right? 100,000, a million times this voltage divider. And you get to pick the value for RE and RF. But they're not going to divide that much. You get your Rn actually multiplied by a pretty big number. What about R out? What happens to R out? So what's your original R out value?
One over GM.
1 over GM. So it's already really small. But because it's a voltage output circuit, it gets divided by that and gets even better. And then for your gain, what happens is your original AV gets divided by your original AV gets divided by this 1 plus T, but this term right here, AV times RE over RE plus RF, is probably going to be much bigger than 1. So you can take this, if you do that, then the 1 goes away and you can cancel out the AVs and you actually get 1 over F, which in this case is RE over RE plus RF over RE, which if you remember for the non-inverting op amp, it's 1 plus RF over RE. That's the gain. That's the gain of your whole op amp. So is that questions on what happened there?
So just to clarify for F, it's just the external circuitry on the outside of the op amp.
Yes. So if you circle all the vanilla amplifiers going from the input to the output, whatever's left is your feedback block. If you're designing your own circuit, then you know where the amplifier is already. But if somebody gave you something that you didn't know, which part is the feed forward amplifier and which is the feedback amplifier, then you go through this process. Okay. So good up to there. Okay. All right. So that's one thing, and this is just the case where your R in and R out are really high. But unfortunately, if you use an RE and an RF, there. Let's look at this. Let's look at the picture again over here. Let's look at a more. Let's go back over here again. So if you look at the output here, it's 1 over GM. This is where the current wants to flow. If you make RE and RF really big, then that's none of the current wants to go through here. All of it wants to go through your common collector, and the common collector behaves normally. But if you used really small resistors, say 1 ohm and 1 ohm for RE and RF, now this current wouldn't be, this circuit right here, or this last stage wouldn't be acting like a common collector anymore, because a bunch of the current would go off this way. So for this feedback block, you treat it just like you've been treating your amplifiers. You want a big R in, so it doesn't steal current from whatever is setting its input voltage, and you'd like a low R out so it doesn't mess up the other side. But okay, so you want this resistance right here to look pretty big compared to whatever resistance is on this node, so this circuit will behave like it usually behaves. But over here, what you want is you want this to be able to provide as much current as this circuit wants. So you want this to actually look like a kind of a small R out compared to this node, which it's not doing right here. So I'm going to stop until I figure that out. But in general, let's look at let's find a more general picture here to okay. So in this picture right here, this this resistance right here is a load to your amplifier. So you don't want it pulling much current if you can. So you want this to look like a big resistance. But this output right here, this should look like an infinite R in, sorry. This R in should be much bigger than the R out of this, so it's not stealing very much current. Just like a regular block, you want a high R in but a lower R out compared to what you're connecting to. Did I finally get that sentence okay? Okay, yeah, you don't want to load your amplifier, so you want these to be big, but you don't want your amplifier to load this, so you want its R out to be small relative to this input. Okay, still can't figure out what my problem is on that last one, but let's move forward. Okay, because again, just like when you say, oh, it's a high R out or a low R out, how you have one word that means a bunch of things, means it gives lots of information, I should say, not a bunch of things. It gives a lot of information. Like my gain is 200, you know that when you move V in this much, you get this much, that V out will move this much. So there's another naming convention. There's another naming convention. So right here, the output right here. So here's the feedback block. The output of your entire circuit is on the same node as the input to your feedback block. So do you see that? So V out is the same voltage that goes into your feedback block. Okay, so if those are on the same node, then that's considered shunt. They're connected together, so they're considered shunt. So if you go over here and the output is shunt, that means your output of that circuit is actually voltage. So let's keep going, and hopefully eventually that will make sense. If you come through the feedback block, here's the output of the feedback block. That's where it's affecting the input. So here's the output of the feedback block. Is that on the same node as VN? No, you have to go through a transistor to get to VN. So this is considered series. If you go up here to the input and you see a series input, that means the input to this amplifier is considered voltage. Okay. So this amplifier right here, as I have it drawn, is actually a voltage input, voltage output amplifier. In other words, a voltage amplifier. And what this tells you, if the output is voltage and the input is voltage, then on the feedback block, whatever the output of your entire circuit was, which is voltage in this case, the input to your feedback block is voltage also. Confusing enough? Okay, so let's and if you have a voltage input and a voltage output, in other words, a series input and a shunt output, the name of this amplifier. If you tell somebody, hey, I've got an amplifier that's a series shunt amplifier, they know that it's a voltage input, voltage output amplifier. So it's the same as saying a voltage amplifier.
How is the input series?
Okay, so you look at the output of the feedback block and you see if it's on the exact same wire as VN. And in this case, VN is on the base and the feedback block, the output of the feedback block is on the emitter. So they're not on the same wire. You have to go through a transistor to get to the other one.
Okay, that makes sense.
So much vocabulary in this. All right, so series shunt. How about this one? What? Here's your V in. Here's your V out. Actually, this RO should be inside the triangle. I should redraw that. What kind of amplifier is that? How about, what's its name? The RO should be inside the triangle. So the stuff that's outside the triangle is R2 and R1. So first question here, since the RO is inside here, is V out on the same term, on the same node as the input to the feedback?
Yes.
Yes. Yeah, R2 is the feedback back to the input. So those are on the same node. So the output is series. So this amplifier right here outputs voltage. Oh, whoops, sorry. Shunt on the output, sorry, my bad. It outputs voltage. Okay, and then this is actually a little bit confusing here, but here's VN. Is VN on the same node as the feedback?
No.
Actually, okay, let me rephrase. Let me rephrase. Do you have to go through a transistor?
No.
No. So this is actually considered on the same node if you don't have to go through the transistor to get there. So if it's on the same node, is that series or shunt?
That's shunt.
Yes. So this amplifier is actually a shunt amplifier. And what kind of amplifier is it then in terms of currents and voltages?
And resistance.
V over I trans resistance. Yes, exactly. So it's a current input VN's contributing some current in, feedback's contributing some current, and that's what determines the voltage at this node. So it's actually current that's being fed back. VN is not setting this node directly. It's the current from VN and the current from the feedback that's setting that node. Okay, how about, one comment here is I have a voltage as an input right here. This to me looks like a Thevenin resistance, but as soon as I see that this is a shunt input, I would change this to a Norton equivalent. I would change the input to a current here. So this is kind of misleading. This resistor right here is misleading. It's treating the input as voltage when it's actually current, which is confusing. Let's go one more practice. What about this one? Kind of ignore this source right here. Just know that this is the input at this node, and ignore RB and voltage. This is the input. So what kind of amplifier is this? How about in terms of series and shunt? I forget if this is animated or not. Let's see. Whoops. It's not animated. Okay. But let's.
I'm gonna guess it's whatever the title was.
Is it shunt input, series output?
Yes, let's see. So I just circled, this is your AV. Everything else is feedback. So is V out on the same node as, can I change colors here? I can change colors, right? Colors, arrow option, ink color. Okay. So this all is going to be your feedback block. Okay. Is V out on the same node as the input to the feedback block?
No.
No, so that has to be series. You have to go through a transistor to get to it. What about the input? Is the input to the circuit on the same node as the output of the feedback block?
Yes.
Yes, so this has to be a shunt. Okay, so in terms of voltage and current, you can come down and look at this table. You see the input is shunt, so what's the input to that amplifier?
Current?
Current. And the output is series, so what's that make the output?
Current.
Current. Yeah, and you can see you've got V out here, but the current coming through here, the feedback block here, once it gets current through it, it's going to change the emitter voltage. And the feedback is actually current input. Right. So did we get it right? Oh, good. Always worries me. How about this one? And again, ignore this over here. That's just, you know that this is the input to your amplifier. So if you circle all the vanilla, so I see a common emitter, and is this a common emitter or is this common collector? V out should tell you.
Looks like common emitter.
Yes, common emitter, because V out is at the collector. So that's a common emitter. So to circle the vanilla circuit, that. And then your feedback is this whole thing. So is the output of the feedback, is it on the same node as the input to the entire amplifier?
No.
No.
Okay, so that's, what kind of input's that?
Series?
Series, yes. because it's not the same node. And what about the output? Is that series or shunt?
Series.
Series, yes, because V out's at the collector, but the input to the feedback's at the emitter, so they're not on the same node, so it's series. And now again, is that voltage input or current input?
Current input.
Series over here. So if you go over here, we've got series here. Which tells you it's voltage.
Sorry, voltage.
And series output though,
That's current.
that's current. Okay, so this is a voltage input, current output. What kind of amplifier is that?
A transconductance amplifier?
Exactly. So hopefully we're right. Yes, we're right. So that's a naming convention that you'll hear. And we're already, what time is it? Let's see. Oh, we're at 2:15. We're an hour, a little over an hour. Let's see. Okay. Let's see if I have. Okay. So this is we've already gone through this. Let me give you a quick picture of what happens when your RE and RF either are too small and mess up your output or too big and mess up your input. So let's look at that. We've already gone through and seen that you circle the vanilla amplifiers and you just multiply all their gains. I don't have a ×1 on here, but for the common collector. So that gives you your gain, your AV, and then we figured out the feedback factor. So that's this value right here. And the calculations that we did before, that's if you have a really big RN and a really low R out. Just multiplying by 1 plus T works great. But this what I'm going to talk about right now is the case where, again, RE and RF, they're either too big for the input. In other words, they get loaded by the input of the amplifier on this feedback right here. So let me get rid of that. So this R out, it messes up your input, or this is so small it pulls a bunch of current off your common collector and messes it up there. So your RE, so either your R out might be too big and your RN might be too small, or there might be a problem with your RE and RF values. I'll try to get through this quickly, and then that's the last topic I have for today. So just loading, okay, that's what we just did. Ignoring loading. Okay. So this is the series shunt amplifier we were talking about. I just drew it in a little bit different way. And actually, let me go to, I put another handout with a little more detailed step-by-step of doing this calculation. So let's use that instead. Okay. So we've gone through that. So now we're trying to look at that series shunt, in other words, voltage amplifier with loading. In other words, that RE and RF are making problems for your amplifier. Either your amplifier is loading your feedback or your feedback's loading your amplifier. Okay, so when you do this, so this is the same amplifier we had before. We had the voltage divider over here. I just kind of bent it in a weird way. When you do this, you get to treat this amplifier as another two-port problem. So remember when you were finding R out, you zeroed V in, or if you were trying to find GM of an amplifier, you zeroed V out. You get to use those same rules when working with this. because it does have gain. The gain is less than 1. It's R4 over R4 plus R5. But you can still treat this as a gain component. Okay, I'm going to keep this really fuzzy, actually. And then I'll make another video that goes through this step by step. But just so you can see what happens, kind of the extra math that goes on when this R4 and R5 are causing trouble for your amplifier. If you are looking for a new Rn, so our original Rn was R pi for the R example. This Rn would be R pi. But it turns out if you hook this up with resistors that are very small, or actually on the order of R pi, you end up with a voltage divider on your Vin. So your actual Rn looks like your regular Rn in series with these two feedback resistors. Okay, so Rn gets bigger. You can see it gets bigger, but you can also see that if R4 and R5 are really big, then the voltage drop across your non-inverting and inverting input, the difference between those two inputs gets very small. So you can see if R4 and R5 are really large, this is a voltage divider, but very little voltage is dropped across Rn, and most of the voltage is dropped across R4 and R5. So if you give an amplifier a smaller input, it's that difference that gets amplified, and now you get less gain. So it turns out if R4 and R5 are too big, this voltage divider gives you much less gain. So that's one problem you can have. On the R outside, what you get is our original RO was 1 over GM, if you remember the example. The original voltage amplifier had a common collector on its output stage, so its R out was 1 over GM. What you end up here is if R4 and R5 are small, then you get a big voltage drop across that 1 over GM, and your V out will get smaller and your gain will get smaller. But if you have a really big R4 and R5, then your V out stays large. So an R4 and R5 that's too little divides your output by a lot and gives you a small V out. But on the other hand, if you make your R4 and R5 too big, then over here, this divider messes up your V in and makes it smaller. So you have to find that R4 and R5 that put it between your R in value and your R out value. So neither gets affected. Okay. Let's try 4 questions and then you're graduated. So try to come up with 4 questions about this. Just in the big picture that I just explained. I didn't go through the math, but just as an aside, when you go through the math, your final result for gain, here's your final result for gain. For your, where's the R outs? Your R outs change by quite a bit, and your R in changed by quite a bit. I don't have it summarized very well here, but yes. Okay, how about 4 questions for everyone? So you have 35 people that you can send off into summertime by asking a question, preferably about the how feedback affects your gain.
So this is something you would use on like the IC level of like making your circuits, or is this something that you would use like when you're making an op amp? I'm a little bit confused.
It would be when you're picking your R4 and R5. You can for any amplifier you pick, whether it's series shunt, series, shunt, series, you can come up with an equation for how you can come up with equations for how R4 and R5 affect your gain, your R out and your R in. And if you have specific specifications, you can say, oh, for this R4 and R5, it gives me my R in spec, but oh, it doesn't give me my R out spec, or it doesn't give me my gain spec. So it's the math that your simulator does.
Oh, okay, so instead of just arbitrarily choosing kind of like ballpark resistor orders for when we try to get the gains of these things to set up correctly, we should choose them specifically to make sure that our R in and R out requirements are like met.
Yes.
Okay, cool. Thank you.
Okay. There's 3 more to go. As you can see, it's pretty complicated here, but this is your gain equation right here. And these aren't right with feedback, so I'm not sure where that went. Ah, there we go. So then you have your loop gain due to R4 and R5. That's pretty complicated, but then you know that your R in is multiplied by 1 plus this whole thing, and your R out is divided by 1 plus this whole thing, and it's a mess. And then you think MATLAB, and you have it do the hard work for you. Okay. Let's see. How about a question on anything today? How about 3 more questions on anything today?
Can I ask a question about, so in my lab, we talked a lot about like the importance of like a capacitor inside of the op amp. How does that relate to like what we've been talking about?
This is pure low frequency response, but let me bring up one more that I forgot to mention. I didn't have that in my list. Okay, so we talked about a compensation capacitor. Do you remember that? So you have the dominant pole and you have the secondary pole. And if you violate Barkhausen's, in other words, at 180 degrees phase shift, you still have a gain of greater than 0 dB. Hopefully that sounds familiar.
Yeah.
Okay, so that capacitor is to move the dominant pole over. So your gain drops below 0 dB. And one thing about, so this is what that single capacitor does. It gives you, this isn't exactly what I was looking for, but it moves that dominant pole over, and now your gain starts to drop earlier, and by the time it gets to the second pole and drops from there, it drops below 0 dB. Okay, that's okay, but if you move your dominant pole over, now the problem is that your bandwidth, so if you move the dominant pole over, the area that you have a constant gain, that gets narrower. So there's other ways to do it. In lab, I am guessing that maybe you put a resistor in series with a capacitor.
Yes.
Okay, so that right there adds a 0, adds a second pole and adds a 0. And so you'll still have a pole, but you can use that 0 to cancel out your first pole. And I'm going to go back over these slides because I have my own questions now about the slides. But by adding an extra pole and an extra 0, you can actually play with the dominant and secondary poles in strategic ways. So you could keep the bandwidth wide, but you can kind of fend off the 180 degrees phase shift for later. But you know, and you can keep going on that. You can have an RLC network on the input as well as in the feedback to do that. But yeah, it's all about moving that dominant pole over. Moving the dominant pole over so you don't violate Barkhausen's.
Okay, thank you.
Okay. I'm not sure if that answered the question. But okay, 2 more to go. 2 more to go. You're doing good on anything today.
Is there ever a time where you might want a high gain or phase margin? Or is it just try to reduce them all the time?
I was trying to do a low power oscillator, and I only needed the oscillator to be on for just a few like milliseconds. And so I tried to make it so I had massive ringing. So if you have a very small phase margin, then you get ringing. And so I tried to use that instead of having like a separate clock or a separate oscillator circuit. I tried just to get the thing to ring like mad just for a little time and then damp out. So if you want it to oscillate for a certain amount of time, that works. There was a Professor Sirovic that retired a few years ago. He taught a class on oscillators and he taught a class on amplifiers. He taught 308. And he said, you know, everybody in my 308 class made oscillators and everybody in my oscillator class made amplifiers. It's just all about where the dominant pole is. So this is a well-known technique to make an oscillator too. Just make it unstable. So was that answer a question?
Yeah, that's pretty neat.
One question and you're free. Okay, that's hard. It's hard to come up with questions. See if there's anything else to say. Folded, we've got, okay, then I guess that's it. If there's any other questions, feel free to email, Zoom, whatever, all summer. I don't have any plans. So also if there's a number of people that wanted to do IC design over summer, if you're interested in that and you'll have time, like you don't have a co-op or something, I welcome emails on that too. So that's all I got. But I'll post a few more videos and you can watch it if you feel like watching over the summer or whatever.
Thank you so much, Tina. It's been a pleasure.
Okay. Pleasure's
Thanks,
been
Tina.
mine.
Thank you, Tina.
It's been a rough quarter.
Tina, have a great summer.
Yes, you too.
Thank you, Professor.
All right. Bye-bye.
Thank you.
Thanks,
Bye. Bye-bye.
Professor.
Thank you.
Oh, thank you.
Thank you, Professor.
All right. Bye-bye.
Okay. I got you. I got you. Can you see us, Tina? Can you see me?
Hey, Carlos.
Hello. It's me and Patrick.
Hi.
Sorry, came a little bit late today. We thought the lecture was for some reason, and then we were working on our 325 or our 329 project, and then we like hopped in like the last 30 minutes. But
Okay.
is this the last one of all of them, or is this the recorded or?
I recorded it. I'm also gonna do another one on Wednesday that'll be basically the same thing. So if you want to watch the video,
Okay. That's what we were another one on Wednesday.
okay. If you have any questions, you can always email.
Okay, so the Wednesday one is gonna be at 1 as well then? Okay, sounds good. We're gonna yeah, sorry, there's video games in the background.
Okay.
The roommates are playing video games, sorry. Yeah, so we'll just hop in. I felt bad. Like my alarm for 2 p.m. went off for our usual class time, and then I hop in and it says 1 p.m. and we're just
Yeah,
sorry about that.
no, it was just the plan that if somebody had a final afterwards, we'd start at 1. So, but all
Well,
good.
we'll see you on Wednesday at 1 then. Yeah.
Okay. How's the 329 going?
It's going pretty well. We got a good portion of the way done.
Nice.
We're doing like a density calculator, like using a water level sensor.
Wow. Okay.
So yeah, it's pretty cool. I mean, we got a good portion of it done, and it's due Thursday, so we still have plenty of time.
Nice.
But yeah, thanks for the portion of the lecture that we watched. We'll see you on Wednesday to get the whole thing.
Okay.
But yeah, I appreciate it. Yeah. Thank you, Tina.
All right. I'll see you later. Good luck.
Thank you.